Section 6, Bypass Power Down Mode. Our basic test sequence has focused on normal filtering operation. We applied a new transaction to the DUT every clock cycle. That transaction included a random frequency sinusoid and a random cyclic mode applied to the DUT inputs. But as we mentioned in section 1, our programmable bandpass filter does include a combined power down bypass mode. So let's extend our basic test sequence to exercise that mode. We'll, after 16 or so trials in normal operation, we'll power down for a few cycles, and then we'll recover and resume normal operation for a few more cycles. We found it convenient in describing the extended test to define these 4 control states. The filter state is what we've been in all along. Bypass state is entered when that most significant control bit, control_bypass, is asserted. And we stay there for 1 or more cycles. And once that control bit gets deasserted, we automatically transition to a 1-cycle wait state. This 1 millisecond state allows time for the supply voltage and bias voltage to return to their nominal levels. We then resume normal operation, and the only difference between the resume state and filter is that resume knows the last packet tag used during the trials, and instead of renumbering the tags starting from 1, it continues from there. We found this made the code much more understandable, and the state names, of course, will be visible in simulated wave view. Here's a simulation run showing the last few trials. On this clock edge, we enter bypass for 4 cycles, followed by a single cycle wait state, and then we resume normal operation. Notice we're numbering the tags from 17 since the last normal transaction was 16 instead of returning to 1. An important point is that during these inactive states, we want to temporarily disable the gathering of coverage metrics, and we'll see how to do that in section 8. And then we re-enable metrics, and so these last 4 cycles will contribute to the coverage metrics overall. Here is the case statement which resides inside our fixture submodule that uses the current state in the current mode as determined by the untimed sequence of tests from the sequence object, uses those to drive the control bits. So here, as we enter the bypass state, the most significant control bit is driven high. When we're ready to recover, we enter wait state, and that same control bit is deasserted. And the state diagram is shown here at the right. It reflects the simulated waveforms we just saw. For example, when the parameter inactive is set to 5, that results in 4 bypass cycles and a single wait 1 cycle, followed automatically by a resume. To summarize, we wrote this extended test as a directed test case. There was nothing random there. We determined the length of the extended test by setting the parameters trials and inactive. And we found the state definitions to help us organize the code and make the details a lot clearer. We'll see in section 8 how to add an if-only-if clause to our coverage group to suspend gathering of metrics during the inactive cycles. And that leads into our next section, 7. We'll see how we can implement portions of our verification plan even during the inactive cycles by writing analog assertions. So stay tuned for section 7.